I do not want to give a very lengthy overview of machine learning. I mean, if you open the news today, you will most likely find some comment on machine learning, some comment on AI or deep learning. All I wanted to say is really that kind of artificial intelligence and machine learning has been around for a very long time. I mean, artificial intelligence has really been studied since the 1950s, and then kind of it evolved into machine learning in the 80s, and really since about 2010 you saw the rise of deep learning in particular, and then it led to many advances, in particular in image processing and the natural language processing, which are really things which you see probably applications of in your everyday life. If you get on your iPhone and you ask Siri something, it will use a deep learning model which was trained on massive amounts of data. So this has really been only coming around in the 2010. It wasn't that neural networks haven't been around. They have been around since the 90s, really, but it just was for the compute power and the amount of data. So deep learning models are very data hungry, and you really need a lot of data to train them, and correspondingly you need a lot of compute power to train them. So now, you know, a lot of stuff happens in the cloud. You have GPUs, which are graphical processing units, which are very good at doing those linear algebra computations which are needed to train neural networks. And kind of only with the advances of these computing techniques was it able to actually train such model. But not only on the computing side, but also on the data side. You can just think about things like, for example, Google Translate. It's a purely data-driven approach. There isn't really any semantic model or anything. It's a purely data-driven approach where we have one sentence in one language and then one sentence in another language, and it's really just about kind of understanding the mapping between them using a black box model. But to train such a model, really you had to first build Amazon Books to be able to have enough data of books in different translations to be able to train those models. And for a long time it only went from really any language to English, and then from English to any other language, because there wasn't enough data, say from German to Spanish, because most of the data was actually going from one language to English and then to the other language. So deep learning has really seen its rise more recently in the last decade, but I just wanted to make you aware that machine learning has really been around for a long time. Nowadays it is really machine learning, what I think most scientists call it. Artificial intelligence is something which is mostly used for people in business. So you see the same topic, but someone on the business side in a PowerPoint presentation will call it artificial intelligence, and then a scientist in its PDF presentation will call it machine learning. So this is really what you see about. If you read the news, it's all about AI, but it's really just machine learning or deep learning in particular. So you've seen a lot of advances, really. I think AlphaGo was a good example. It uses reinforcement learning, but again, you needed a lot of compute power to be actually able to train such a model. But you've seen the result and how good it actually performed in practice. But having spoken about all the kind of good things about machine learning and where it is helping, there are obviously also some downsides, in particular in deep learning, which has been so much on the rise recently, which has had so many headlines in beating image competition, beating natural language competitions, but it's also very much black box. So sometimes it's very difficult to understand how the neural network is actually coming up with its predictions, and there's where a lot of areas such as explainability, interpretability come in, where researchers are working on right now. Another thing is also the ability to sometimes throw off very easily the neural network. Sometimes you can take an image and you change a single pixel and suddenly the model comes up with a completely different prediction, and there are actually models which are called GANs, which are used to kind of find such weaknesses of models. And that's obviously a problem, and a lot of the current research in the neural network area is really about kind of understanding better what the model is doing, how it is coming up with its decision, but also making it more robust. That's obviously very important if it is applied in safety critical applications such as self-driving cars, as is mentioned here at the bottom. So we really want to have those models more resistance there, and there's a whole branch of deep learning which is called Bayesian deep learning, where people kind of try to bring back uncertainties into deep learning models, which is very, very helpful and has solved some of the issues with those kind of pathological predictions of deep learning model. But kind of with all this fancy words and hype about deep learning, which probably you've read a lot about as well. I mean, probably otherwise you wouldn't be doing this degree and being in this course. But it is sometimes also important to just be a bit down to earth and remember that no matter how fancy the deep learning model is, no matter how fancy the terms are called, like attention layers or recurrent neural network, it can sound very, very abstract and fancy, but it is just a very simple mathematical mapping. And I just wanted to point this out in this one slide. After all, any neural network architecture is just a supervised learning model. It's really just a mapping between some input data on the one hand and some output data on the other hand. So I train this model, and if I have a given data point, obviously here's just one dimensional, but think about any very arbitrary high dimensional space, say an image. I want the model to come up with a prediction of given type. In this case, I just shows a continuous variable, but it can also be a classification problem, in which case it could be a probability. What would be a probability of a pedestrian being in front of the car? But what is really important here is that sometimes in the ideal case, you really also want the model to have some uncertainties, and also you want the model to be able to kind of say that in a region like here, where you haven't really seen much data, you want the model to kind of, it might still give you a prediction, but you really want the uncertainties to increase. So it should be aware that actually the model isn't that good in this region. But kind of that said, just don't forget that a machine learning model, a supervised model, is just a mapping. It's like y equal to f of x. I have x here and y here, and I really just want to learn this mapping, learn this function f. So the neural network is just one way of learning such a function, but it's just good to keep that in mind, because sometimes things get complicated, and it's always good to just go back to the basic and remember, well, actually all I'm doing here is trying to learn a function f which maps inputs to outputs there. And this will really apply to any supervised learning model, and it often helps if you get lost to just remember this little fact. Also, I've just talked a little bit about deep learning, which is kind of quite a hype these days, and kind of everyone wants to be working in deep learning. I just wanted to say there isn't really any free lunch, and there actually exists a mathematical theorem which is called the no free lunch theorem, which says there isn't any one model which is kind of good across the board. For specific cases, there is always one best model, and for another case there might be another best model. This is why it's important to kind of, for you as a data scientist, to really know about all the kind of variety, or this, you see this zoo of different models, so you know, okay, for this case really this model might be best, but for this type of data maybe a boosting model, here a convolutional neural network. You really have to have a good understanding of those models, because it doesn't help if you always apply the same model. You really have to understand the variety of models, and also what are their strengths and weaknesses. It's not just about being able to implement it in Python, say, okay, this is boosting, this is what I write in Python to get this model. You really want to know what are the advantages of using this model, what are the disadvantages, when does it really excel, and when does it perform poorly. And this is something which I want to try to cover as well in this course. So it's really important. Obviously you have to know a little bit of the math behind it, you have to know how to implement it, but it's really important that you understand the kind of intuitive picture of those models and have a better understanding when you can actually use them best.